So I'm representing my group from UC Irvine. I'm Jeff Krichmar. I spoke a little earlier this morning. And this is work by Carlsen, Mike Baylor, and Nick Dutt from the departments of cognitive science and computer science. So I'm going to talk about our simulation environment, which is GPU accelerated, and give you a couple examples. One application example of a neuromorphic application, and another of a framework that we've developed to automatically tune spiking neural networks. So I guess I don't need to do this slide. What are spiking neural networks? We build networks, large-scale networks of spiking elements. Excuse me, it's hard to see this, so I'm going to go back and forth. So why use them? I talked a little this morning. Spikes are rare events. There's a temporal code. What I didn't talk about, well, I talked about plasticity this morning, but spiking networks support spike timing dependent plasticity. And that's a nice, stable, unsupervised learning rule that's biologically inspired. And they're event driven, and so that makes them computationally efficient and energy efficient if you're on hardware. So what are the tools of the trade that we're using? When I do this, because I can't see, do you see my mouse pointer? Good. Okay. So we're using the Izikevich simple neuron, or either the 4 or the 11 parameter neuron, which is a nice dynamical system neuron that you can change just a limited number of parameters and get different spike waveforms, which is very nice. We're using spike timing dependent plasticity. I don't have time to go into it, but the temporal order of spikes actually leads to whether you get long-term depression or long-term potentiation. And then we also include short-term plasticity, where there's presynaptic short-term facilitation, short-term depression. So we're using a bunch of these tools in our environment, and this I'm sort of ashamed to put up because it's by no means exhaustive. These are a few of the neuromorphic hardware platforms out there, hardware devices or platforms. And you can see, just looking at this busy table, some they're all spiking. Some are digital, some are hybrid digital analog, some support plasticity, some don't. But the point is, there's a bunch of platforms out there. They're using a similar address event representation, as I said before. And similarly, this is by no means an exhaustive list, but there's a bunch of neuromorphic tools out there that we've talked about so far. And the one I'm going to talk about, of course, is my own, which is Carlsen. And I should say to Carl, our lab is the Cognitive Anteater Robotics Laboratory. Our mascot's the anteater. Don't ask me why. It's not clear. There's never been an anteater in Southern California, but it makes for a nice acronym, Carl. So Carlsen, and our robots are called Carl, various names. You'll meet one later. So what's nice about ours, we're using GPUs in the CUDA environment. So it's very easy to use, very easy to put on your own machine, so it's quite available, off-the-shelf stuff. It is compatible with neuromorphic hardware. It supports learning. It's quite efficient. I'll show you some examples of that. And one thing that's very new that I'm going to show you is and it has a Pine-like interface. Someone mentioned Pine. Because it's in CUDA, it doesn't run Pine exactly, but it looks similar. So if you're used to Pine, you can use our system. One thing that I will talk about today a little bit is we have an automated parameter tuning framework that we just published, and everything I talk about today is publicly available, and you can download the examples, and I'll put up the website right now at the very bottom of here. I'm not going to go through these, but just to show you that we have used this for a variety of different applications. So it shows the kind of general purposeness of our system, ranging from attentional aspects to visual categorization to object recognition, and also homeostatic plasticity. So the first application domain was a paper by Mike Baylor from our group that just came out last year, and it was on a large-scale simulation of motion perception, cortical motion perception. And if you ever have to do some motion perception of continuous video, you know how computationally intensive it is. But it's something that we do very naturally. We work our way through the environment. You see up here, you get this spoke of expansion of where you're heading. We do this seamlessly without knowing. Imagine if you're going through a cluttered environment and trying to track an object. We can do that very nicely and easily because we have this motion perception ability that sometimes we just completely take for granted. Now down here, we also have to deal with, this is an illusion, but we have to deal with occluders. So if you move this rectangle to the right, you actually see the component of that motion going upward. And so that's an illusion, but actually it's important for us to deal with this. So we tend to pick up perceive the whole global pattern of motion, which is very important if you're tracking something through a cluttered environment that's going behind occluders and such. So what parts of the brain do that? Well, it starts in the retina, but I'm showing the cortical areas. There's V1. It's hard to see, so I can bear with me. So there's V1, V2, and then leading up to a very overstudied area called MT, which has so there's direction selectivity in V1, but you have neurons that are motion sensitive and speed sensitive in area MT, and then these lead on to parietal cortex and area MST that actually give you combined parts of a motion that give you certain perceptions. Now in our model, which is a spiking model, we start with the video feed, and then we classify this in 3 different speeds, and then we have two types of V1 cells, simple cells and complex cells that are spiking neural network cells, and these feed into 2 classes of MT neurons. Some that respond to the pieces of the motion, component, and some respond to the overall global motion. And the model actually, then in one of the studies in the model in the public, I won't go into, but had a decision layer of parietal cortex that was responding to random dots moving across the screen and actually replicating a psychophysical experiment. So what is the model? What are the guts of the model? So we're using the Simoncelli and Heeger motion energy model at the front end. So in the CUDA environment, we're actually doing at the V1 level, we're actually doing a kind of a rate-based motion energy model, and we have banks of spatial temporal filters. I won't go into the details now because it would take a whole hour to talk about it, but it's a well-established model. It covers a lot of psychophysical data, a lot of recording data for motion perception at V1. They had a rate model at MT, but we wanted to use the speed up and the neuromorphic compatibility of spiking neurons. So we made a 2-stage model of MT with Izakevich spiking neurons. Let's see, this model is larger than that now, but the published model had over 150,000 neurons, 40 million synapses. It was running in real time, so it was responding to video frames in real time. And that was a 32 by 32 frame rate. We actually can do better than that now, but that's a story for later maybe. We used conductance space, so we actually model the synaptic ion channels, which is important. There's a lot of integration and fast and slow currents coming through that actually are important for the computation, so we wanted to make sure we model that. And then we have 2 types of cells. We have the component cells that are responding MT, that are responding to the components of the motion, and then we have pooling over that based on some data from Rust's group. We have pooling over that a bunch of cells that actually are picking up the pattern of motion. So what do I mean by that? So let's see if this works. And let me pause it for a sec. Okay, so what you typically do is show sinusoidal gratings that come across, and these gratings are currently moving across from left to right, and you see a strong response of our component cells firing very rapidly to the rightward motion, and some that are responding to not the preferred direction, but responding nice and graded to things that are moving in their roughly the preferred direction. You see on the bottom the component on the pattern cells, they're also responding very strongly to that rightward motion. Now if I continue, let me just jump ahead. So you can see responding to different components and sinusoidal gratings. But what happens, and this is what neuroscientists and psychophysics people do, what happens if you combine two sinusoidal gratings? So your perception, your perception is actually that it's moving to the right, okay? And that's what we perceive, and that's what these pattern cells actually respond to if you record from them. But actually it's made up of multiple components because I got two sinusoidal gratings going in two directions. And so the component cells, if you record it from them, are responding to that. And that's quite nice that we can actually replicate this finding in this model and in real time. Okay. You get the idea. All right, so why is this good? Like I said, it's computationally intensive to do this kind of video processing, especially doing this motion energy model and this kind of a perception. But where we fall into, here's the Seeger and I knew I'd say Seeger and Himicelli. Heeger and Simoncelli model, or SNH model, and they have a MATLAB version that you can download, but it can only do a limited number of neurons, and it certainly can't do well in real-time domain. It can't do that. And I won't even talk about the memory consumption of this thing. So it's not tractable. Whereas our model, we can get 150,000 neurons running in real time at the right frame rate. And actually, we can get now up to 200,000 neurons with larger frames running in real time. So we're doing quite well. The speed-ups over a CPU are up to 30 times faster than a CPU if you run this GPU implementation. And there's practical reasons, and we're working towards this, where we've actually, get this going, we actually have a smartphone robot called Le Carl, because it was made by a French postdoc in our lab, and it's actually a clever idea. So we're using all the processing and computing capability and the sensing capability of the smartphone, putting it on an RC car with a small board to link them together. But for the point of today's talk is, in this we actually recorded video from the camera and then ran it through our model of MT. And you see all these little arrows, and at each pixel there's basically a summation of 8 cells, and the direction of that arrow is the population direction, and the length is the population vector at each point in this picture. And hopefully you can see that there's a focus of expansion as this Le Carl robot is going down this sidewalk. So it's actually, in a sense, if I had a readout mechanism, I could actually compute the heading of where Carl is going, so where Le Carl is going. So this is actually really promising, and actually we're very close to having this closed loop and running in real time instead of taking the video feed and running it through our model offline. So that's coming soon. And actually, this is an old video, so we have much better responses than this to actually figure out where the robot's heading, and also if there's an obstacle in its path. Okay, so that's a neuromorphic application that kind of highlights what you can do what you can do with off-the-shelf hardware. This would really be nice to actually have on a real neuromorphic chip because of the form factor and the energy consumption. But at least we have like a proof in principle that we can run these neuromorphic applications. And this is just one application domain. I'm going to switch gears in the remainder of the talk and talk about something that we've wanted to do for a number of years now. And that is, you build these networks, and I don't know how many of you have done this, but you spend weeks, months, years trying to tune them until you get them to work. And that's always drove me crazy. And as we get more complexity in these networks and want to make them do better things, it's becoming intractable. So we've come up with a framework to deal with that. And our framework is actually leveraging two things. One is GPUs. So we're using the parallelization of GPUs. And the other is some recent work in evolutionary algorithms, or work over a number of years in evolutionary algorithms. And combining that, we actually can actually search parameter spaces very quickly. And we feel now that we also have a biological principle that actually can guide the search. So let me give you the architecture. And this is your typical, evolutionary algorithm architecture. So you have some initialization, you have an evaluation stage, and you run your evolutionary algorithm based on a fitness function, and then you decide, is that fit enough? All right, then I'll select the best ones, come through again, and keep iterating through this. So finally, you get a population of very fit individuals, and then you can stop. And that's a nice way that people have actually searched difficult parameter spaces. Now what we do that's a little different, I mean this has been done for a number of years, what we do different is we expand this, and so we load onto the system a bunch of spiking neural networks. And since we have the GPUs, we can run the spiking neural networks in parallel. So we get a bunch of spiking neural networks running in parallel, and then we evaluate the networks with a fitness function, and then decide if this population is fit enough, and have we tuned the parameters so we have a working spiking neural network. And the trick with evolutionary algorithms, as anyone who's played with them knows, is that what do you do for your fitness function, or objective function sometimes called. And so what we came across recently, which Paul Glimcher actually kind of revisited, it's not exactly a new idea, but he's actually revisited it with other brain areas, the idea of efficient coding hypothesis. So what does that mean? So actually neural systems adapt their responses to actually gain more information out of the world. And they do that in several ways. They actually decorrelate signals, they have sparse responses, and they adjust to span the stimulus space. So it's a really nice concept that actually fits with any, I would say, a canonical rule that actually goes on in cortex. I'm not sure about outside of cortex, but you look at just about every area of cortex, and it's doing these things and actually gaining more information and self-adjusting. And it goes back to also divisive normalization, and Heeger and Carandini also have talked about this. But Glimcher recently started applying this not to just the visual system, but also the parietal system and how you evaluate value. Anyway, we can take that idea and put it into a fitness function. And I don't really need to go into this, except that we can actually redo this efficient coding hypothesis in a fitness function that you could work and use in an evolutionary algorithm. And we think that you can apply this not just to the example I'm going to show you, but to many examples. And I don't have time to go into all the details here, but here's the idea that we're going to take a bunch of sinusoidal gratings, and we're going to pass it through our system, and we want a set of neurons to actually respond to the different gratings in a way that spans the stimulus space and also sparsely so the neurons aren't firing too much, and finally that each neuron is only responding to one, preferentially to one aspect of the scene or one type of grating. All right. Now the interesting thing about this is rather than trying to do what's known as direct encoding, where we search the huge space of weights or synapses, what we're going to do is do an indirect coding. So we're going to search the smaller space of the parameters for the STDP and homeostasis learning rules that we have. And so instead we only have 14 parameters to search. And so what we're actually doing is searching to make this network better at learning is the short idea of this. So this, during a training phase, we give it a bunch of sinusoidal gratings, and then during a testing phase, and then we allow the STDP and homeostasis to actually learn, and then during the testing phase, we see how well it did to respond to this and how well it fit that fitness function I showed a few slides earlier. And so over time, actually, the population as a whole becomes very fit. So the optimal fitness would be a 1. And so we're running a bunch of networks in parallel, and we run 257 generations, and it took 127 hours, which is not as long as if you had to do this by hand. And you see as a whole, the average group actually became quite fit. And then if you look at the synaptic weights after that evolution, you see that they actually respond nicely and to like become something like a Gabor filter. and you see here's 2 now, so it's spanning the space, showing preferred responses to upward, preferred responses to oblique, and this one's evolving to preferred responses to right oblique. All right, so doing very well. And I should say it's robust, so we ran 100 different iterations of this, and 76% of the time it actually converged to the solution where it looked like this. The other 25% of the time, it usually had bimodal kind of responses, which probably do happen in real visual cortex, but we were looking for kind of Gaussian tuning curves that you see in V1 simple cells. And so the red is the ideal Gaussian tuning curve in V1, and the blue is actually the fit that happened after this automated tuning process. And what's nice about this is we can run 30 or 40 configurations together in parallel, and we get a speed up over the CPU of up to 60 times. So we actually get very impressive speed ups. These are somewhat small networks, 1,000 to 4,000. But what's nice about this is once you've tuned this, you could build it, use that as a building block to tune the next level is one idea. Another constraint is when you do this, we're running on one GPU. We actually are now moving towards multi-GPU processing, so we could do multiple things at once. So with the GPU we're running, we can only fit so many networks of so much size, but that's going to get bigger. GPUs are getting better, and the multi-GPU systems are getting easier to use. Okay, so let me wrap up and then get to some conclusions. So I should give thanks to my current group, the Now group. Let's see, who did I talk about? Michael Baylor and Nick Dutt, my longtime colleague that's worked on all this neuromorphic work. We were part of the HRL Synapse team, so we've worked together on that. Michael Baylor did the motion energy, motion perception model. Chris Carlsen was the brains behind the automated tuning framework. Nicholas Oros developed the LaCarl robot platform, which is another story for another day, but actually a nice, interesting, cheap, but very powerful robotics platform. And then I should also thank some of the people from the group that kind of led to this result, these results. Jay Murakanaka Nagaswaran did, as one of the chapters of thesis work, he did the automated tuning framework, and then Chris followed up. And Jay and Micah Risher were key in actually developing the GPU acceleration of these systems. And then Mike Avery did a lot of work on the HRL Synapse project, a bunch of neuromorphic applications I didn't have time to go into. Okay, so last slide, and then I'll take some questions. So, we've come to the point where large-scale, complex, realistic brain networks are definitely necessary for building these neuromorphic applications and building things of practical value. And the flip side, and actually Todd said this is I'm always straddling that. So I'm trying to build practical applications on the one hand, and then on the other hand, I'm trying to really, I got into this field because I really wanted to understand how the brain works. So this allows me to test theories. And I should say, we were talking at lunch, but what I teach my students is you understand through building. So I think you can do both of these. I try, but it's not easy, as Todd said. So to address this challenge, we've developed tools because I really want to get on neuromorphic hardware, but someone else said this morning, it's, every piece of hardware is different. It's not at a different stage, and at this stage it's hard to work with. We've got to develop tools. So we built this as a tool because we had to hit certain size networks that could do something, so we actually built the GPU tools. But now I'm actually quite happy the way it's matured, and so we're making it available for anyone to use. And I think it's actually important. I've always wanted to do this for a number of years, to build some sort of automated parameter tuning framework. I've done modeling for years, and it's, especially in the spiking domain, it's really hard to put these together and get them stable. So this is a nice way, I think. And I like the fact that we're following on a biological or neurobiological principle, the efficient coding hypothesis, to guide this search. So I feel very good about that. And everything I talked about, the examples, the framework, it's all publicly available. Please download it, give us input. We're going to keep churning this out. As we do more and more new work with this, we'll keep making the new releases available. So that's a good time to stop there. Thank you for your attention again, and I'll take any questions.
So can you speak to how general the the efficiency of the GPU is across different neural circuit structures and so forth? So the example you had, the more kind of V1 to MT example, it seems to do great. Is that going to be for all configurations, like recurrent networks, or is that more hierarchical?
You're going to allow me to advertise. Where's that? Yeah, we've used it a bunch over. There. We've used this on a wide range of problem domains, and it's done very nicely. And I should say that we aren't the only ones that have done GPU accelerated. So we worked closely with HRL as part of the Synapse group. They had a huge GPU cluster, and we did some of this visual stuff. We got a group that was doing hippocampus work, a group that's doing prefrontal cortex work. So it actually does a really nice job. The problem is it takes a lot of power and heat, so that's an issue. So it's not a good thing. Especially I like to think of myself as a neuroroboticist, so it's not a good solution for the embedded class of problems.
Really interesting stuff, Jeff. So just to comment quickly, so we've likewise gotten accelerations with GPU from Hodgkin-Huxley compartment models to hierarchical models of cortical systems, and that 80x speed up versus a CPU is what we saw in the early going. The question I had, among many, I'll just put this one to you. So that first round, I love the use of evolutionary algorithms to do parameter search. We also found that very effective in a lot of settings. The simple cells. Okay, so I know you want to go, so what about going beyond that? I know you alluded to it at the end. Have you tried to iterate that or change parameters to get complex cells, which is pretty readily doable?
You're talking about the parameter tuning framework.
And about the self-organization of the wiring that led to the coding, and how far have you taken that a little bit further?
Yeah, we're in the process. We've really just started. This is the first step in a much larger project. So we're actually working, you mentioned Giorgio Ascoli when we were talking. We're working with his group because we want to model hippocampus. Mike Baylor wants to do further areas down the stream of motion perception using this framework. And then we've had several groups actually approach us with other problem domains. So it's a little early to talk about that, but we're hoping that it generalizes. That was the pitch, and we'll see. But I think it will. I feel good about that.
Great.
I have a question concerning your evolutionary algorithms. What is your choice of genetic operators? Are you using crossover and mutation, or only one of them? And are you doing single objective or multi-objective optimization?
I wish Chris was here to answer that. So we're using single objective, but actually we're working with Ken DeYoung now on multi-objective fitness functions. And I think it's a mutation crossover. There's actually...
Is that in your paper? Then I read it.
It's in the paper.
Okay.
And actually what we're using is an off-the-shelf thing called evolved objects. But I can't remember the actual details. There's a lambda comma and a lambda plus.
Okay, I'll look in your
yeah,
paper.
look it up. I'm sorry, and I can look it up for you right afterwards.
Do you have any gut feels to whether an FPGA would be as good as a GPU or better or worse?
Different, I suppose. So the reason we're not using FPGAs is the CUDA environment's much more approachable. Has, in my opinion, better development tools to do what we want to do. But if we wanted to go to something low power or embedded, then we probably would look to something like FPGA. But maybe I'm wrong, but the last time I looked, there was still the VHDL stuff and not as many tools to actually build the applications we wanted.